can see now it's 5 p.m. Sure, I started recording. Excellent. So, Tuan, are you ready to start? Yeah.
Yeah,
So it's my pleasure to introduce Tuan Pham from the University of Edinburgh, and I'm sorry for the pronunciation. And Tuan will speak about the orbit method for the centerless Virasoro algebra. Thank you.
yeah. Thanks, Stefan, for introducing me, and thanks the organizer for inviting me to speak at the seminar. So this is like um, the project I had last year during my Edinburgh. Yeah. So today I'm gonna tell you about the orbit method for the centerless Virasoro algebra. Um, So the talk will be in three parts. So first, I will recall the classical orbit method. Um, and also, I'm going to introduce you the main object of the paper, which is the Virasoro algebra and the centerless Virasoro algebra, which is also known as the Witt algebra. Um, then I will explain the orbit method via Poisson primitive ideals and why we have to go via that via the Poisson primitive ideals. Um, then lastly, I'll explain what we know so far about the primitive ideals of the Witt algebra and the Dixmy and the strong Dixmy map for the Witt algebra. Yeah. So so first, I'll set up some notation throughout the talk. So all vector space and Lie algebras are over C. So everything I say here will work for an algebraically closed field of characteristic zero. But yeah, for the simplification over C for now. Um, and let G be a Lie algebra. So here, the only restriction I have on G is that its dimension can be finite or countable. And then let EI be the order basis of an order basis of G. So usually in ring theory, we want to study representations of G, and then in doing so, is like the natural thing is to look at modules over the universal enveloping algebra. Um, so the universal enveloping algebra is defined as follows. So it is um, it is the free algebra generated by the basis EI, quotient out by the relation defined by the bracket. By that, I mean the commutator EI EJ minus EJ EI is equal to the Lie bracket of EI and EJ. So a good way to think about the universal enveloping algebra is non-commutative order polynomials in the EI. So this is by the BBW theorem. A C basis for the universal enveloping algebra U of G is the product of EI1 to the A1 up to EIN to the A, where EI1 is less than EIN because I have an order basis and the EIs are in my basis. Cool. Right. Yeah, so as I hinted before, so whenever we have like an algebraic structure, one of the one of the thing we want to learn is representations of it. So this allow us to use like linear algebra to better understand our algebraic structure. So in other words, what we want to learn is to understand the representation theory of the Lie algebra G. Yeah, but compared to so like so I'm coming from a ring theory perspective, so I don't work a lot with non-associative algebra, but instead we want to turn it into an associative algebra U of G. And then studying representation theory of G is the same as studying modules over the universal enveloping algebra. But in general, it is difficult to understand or classify all simple modules in this case. For example, take the Lie algebra, the second Lie algebra. The second Lie algebra is a simple ring, so there's no but like it's representation theory is really hard to classify or understand all. Um, so instead, we're gonna slightly modify the question in the following way. So a two-sided ideal Q of UG is co-primitive if Q is the annihilator of a simple modulo M over U of G. In other words, U is the collection of X in U of G such that X Qs M. Qs a modulo M, and M is simple. So now, so this is the idea of Dixmuir that so instead of like trying to classify or understand modules, we want to understand sort of their primitive ideals instead, the things that kills them instead. So our refined question now is to understand the primitive spectrum prim of U of G, which is the collection of all primitive ideals of U of G. Unfortunately, this is like still a little bit hard to understand. So we seek some kind of correspondence. And the correspondent I'm heading towards is the orbit method and the Dixmuir map. So let G be the adjoint group. Let big G be the adjoint group of small g. And then note that this adjoint algebraic group acts on the dual space G star by the coadjoint action. And then we denote the space of orbits by G star coadjoint by G. So this is also known as like the coadjoint orbit space. Yeah. So and in the 60s and 70s, Consul Dixmuir, Duflo, Matthew, and Ressler together they proved that if G is a finite-dimensional solvable Lie algebra, then there exists a bijection between the space of coadjoint orbit and the primitive spectrum of U of G. And this map give us a way to understand primitive spectrum of U of G because the space of coadjoint orbit G star coadjoint is much easier to understand. So in fact, so I should say that this is in fact a homomorphism. So there is a Zariski, the quotient Zariski topology one can put on the coadjoint orbit space, and a sort of Zariski, or also known as Jacobson topology, you can put on a primitive spectrum space, and then yeah, it is proven that dx bar is also a homomorphism between them. But for the purpose of this talk, we're just gonna consider the space without the topology. So a natural question for us is that is there such a map for the Virasoro algebra? So we want to understand the primitive spectrum of the Virasoro algebra, or is so yeah, the natural question is there such a map for the Virasoro algebra? So what is the Virasoro algebra? So first, I'm gonna explain you what is called centerless Virasoro algebra, or also known as the Witt algebra. So, so it is the Lie algebra of derivation or Laurent polynomials. So as a vector space, W is just Laurent polynomial times this element del, and del is just the operator d over dt, which is like taking derivative with respect to t. So as a vector space, it's just Laurent polynomial times del. Now I'm gonna equip it with where the Lie bracket of f del and g del it's just f g prime minus f prime g times del, and g prime and f prime here just mean taking derivative with respect to t as well. So W has a nice countable basis where I let the EI to be t to the I plus 1 del, where I range over all integers and the Lie bracket of EI and EJ. It's just j minus I times the another basis e I plus j. So yeah, the bracket has a particular nice form in this basis. So the Virasoro algebra Vir is the unique non-trivial central extension of W. Um, and both the Virasoro and the Witt appear, and they are essential in physics, in conformal field theory, and vertex operators algebra. So there's a lot of story about um, quantum field theory or like conformal field theory that like the Virasoro appear and yes. So yeah, that's why we want to study the Virasoro representation of the Virasoro or like representation of the Witt algebra. Can you guys hear me now?
Yes,
Yeah.
yes, yeah.
Yes.
Um, cool. So, however, we have a problem. Um, However, we have a problem that the Witt and the Virasoro do not have an algebraic adjoint group over C. So obviously the Witt algebra is also the Lie algebra of vector fields on a circle, but over C, this is not the adjoint group of W. So we need a slightly different approach. Okay. Cool. Are there any questions for this so far? Cool. Then, yeah, then, so the different approach I'm hinting towards is using Poisson primitive ideals. And so in the next section, I'm gonna explain what I mean by that. Yeah. So, so a Poisson algebra A is a commutative algebra with a Poisson bracket, which easily bracket. So in particular, it satisfy in particular, it is bilinear, it is anti-symmetric, and it satisfies the Jacobi identity. But moreover, um, the Poisson bracket interact nicely with the multiplication in A. So in particular, what I mean is the Poisson bracket of the product xy with z decompose into the product of the Poisson bracket x and z and then times y plus the Poisson bracket of y and z times x. So a good way to think about this compatibility condition is that the Poisson bracket is a biderivation. So when we specify to one variable, so the Poisson bracket with z, for example, this is now a derivation. And then the above equation is just the Leibniz or the product rules when you take derivative. So now the symmetric algebra as an algebra S of G is just isomorphic to commutative polynomials on the EI on the basis EI, and it is a Poisson algebra. Um, so the Poisson brackets is called is defined by letting the Poisson bracket of x and y to be the Lie bracket of x and y, where x and y is in G, and then you extend this to all of S of G by this product rules, by this product rules. So the reason why we're interested in the symmetric algebra S of G is that S of G is the associated gradient of U of G, and lots of the time, nice property of S of G can pull up to nice properties of U of G. Like for example, if S of G is Noetherian, then we can prove that U of G is also Noetherian. Uh, yeah. Okay, so an ideal of S of G is called Poisson ideal if I is closed under the Poisson bracket with S of G. So this is just the generalization of a Lie ideal. And yeah, so in particular, I is both a Poisson ideal is in particular an ideal and a Lie ideal um, of S of G. We also have that. So remember, recall that our G is finite dimensional or countable dimensional. So S of G satisfy the generalized Nullstellensatz. So Nullstellensatz sort of works for when G is finite dimensional, but then you sort of can extend it to countable dimension. Um, so it works for our G here. So S of G satisfy the generalized Nullstellensatz, which means that element of the dual space G star, so chi in G star correspond to maximal ideal M chi in the symmetric algebra, where this ideal M chi is just defined as the kernel of the evaluation homomorphism S of G to C. Okay, so note that a maximal ideal M chi here need not to be a Poisson ideal. So what we want is we want to take the maximal Poisson ideal contained in M chi, and then that's what we call Poisson primitive ideal. So a Poisson primitive ideal is where you take a maximal Poisson ideal contained in a maximal ideal. And now we can form the Poisson primitive spectrum of S of G. So which is the collection of all Poisson primitive ideal P chi, where chi is in the dual space G star. So what we've done so far is we define a canonical map from T star to the Poisson primitive spectrum of S of G, where I take chi and then I send it to P chi, which is the maximal Poisson ideal contained in M chi. Cool. Are there questions for this Poisson primitive spectrum? Cool. Right. So this in particular give us another way to think about the correspondent um, or like the orbit method or the Dixmy map. So recall before we have that the space of coadjoint orbit G star small G star quotient out by G is isomorphic or like homeomorphic to the primitive spectrum of U of G, where G is a finite dimensional solvable Lie algebra. So this is a bijection or homomorphism. And so this is a theorem by this is the work by Gordo that in 2010 or like and also like this is based on the work of I guess Ken Brown and Ian Gordon in 2006 as well that when G is a finite dimensional Lie algebra over C then the space of coadjoint orbit G star quotient out by G is homomorphic to the Poisson primitive spectrum of S of G. So thus we have um, thus when G is a finite dimensional solvable Lie algebra, we have a homomorphism between the Poisson primitive spectrum to the primitive spectrum of U of G. So this map, the X triddle here. So note that the algebraic group G is now a homomorphism, dx twiddle. So now we can apply this to a more general setting. Like for example, when we do quantum groups or like deformation. Um, yeah. So I'll go now slightly modify as follows. So we want to study the primitive spectrum of U of W. So everything I say here from now on will so everything here works for the Virasoro algebra as well as the Witt algebra. But for the simplification, I will explain it for the Witt algebra. It works exactly the same for the Virasoro algebra. Yeah, but if there's time at the end, I'll explain how it works for the Virasoro. So we want to study the primitive spectrum of U of W and construct the strong Dix-Mean map. So this map dx twiddle here, I'm gonna call them the strong Dix-Mean map. And construct the strong Dix-Mean map dx twiddle from the Poisson primitive spectrum S of W to the primitive spectrum of U of W. Right. Are there any questions for this? Yeah, and one more reason why we want to do this is that because we want to sort of understanding the primitive spectrum of U of W. Um, via the Poisson primitive spectrum. So this Bay Poisson primitive spectrum, they're really well understood in a paper by my supervisor Sue Sierra and her collaborator Alexei Petukov in 2023. So they prove that in particular this Poisson primitive ideal P chi is non-zero if and only if chi is a local function on W, which I'll define below. And they also characterize exactly when you have the two the so when you have the two same ideal P chi equals P eta for chi and eta in W star. So what I'm saying is that this space of Poisson primitive ideals is sort of well understood. And then once we can this map, hopefully we can pull back what we want to understand from on the primitive ideals of U of G from the Poisson primitive side. Okay, so now I need to sort of explain what does it means to be a local function. So first, a one-point local function, chi, and then it depends on the following parameters, x, alpha 0 to alpha n on W, um, as follow. So the x here is the base point, and alpha 0 to alpha n is the parameters. So chi of x alpha 0 to alpha n is a linear map from W to C, um, where it maps f del, an element f del, to alpha 0 of fx plus alpha n of f to the nth derivative. So this notation means f to the nth derivative, and then evaluating at x. Um, so where I'm here for some technical reason. So remember that W is so there's W is Lorentz not polynomials time del. So that's why I need to sort of assume x is non-zero. And then for we want to also assume alpha n is non-zero. And n here is called the order of chi. So an example of a local function is just like, for example, chi x 0. This is just like an element of the dual space W star that sends f del to the first derivative of x, of f evaluated at x. Right. And in general local it's just a finite sum of one-point local function chi I. And then here I'm just assuming that the base point xi and xj are different. Okay. Any question for this part? Cool. So yeah, so with that now we are equipped to sort of define the primitive or like define a subset of the primitive spectrum of U of W and understand the strong Dix-Mean map for W. So first I'm gonna tell you a construct primitive ideal from local function. So this is known as like the orbit method, or also known as like, yeah, I think this is best known as the orbit method. So let chi be a local function on W. A polarization P of chi is a finite codimensional subalgebra P of W, and at the same time, P is a maximal subspace such that chi vanish on the derived subalgebra. Cool. Um, so now chi induce a one-dimensional representation of P, which we write C chi, and the induced representation. So now we have a one-dimensional representation of P, and now we want to sort of induce it to a representation of W, and then we do that just by tensor with U of P, with U of W on the left. So, and this induced representation, M chi P, is called a local representation of W. And then I'm just taking the annihilator of that representation. So the annihilator of U of G, and then calling them Q chi P. So yeah, so for the expert in the audience, here I'm sort of slightly lying a little bit. Um, so this is only the orbit method for nilpotent Lie algebra. So for Lie algebra, you need to sort of introduce a twist to this one-dimensional representation, and then text the induced representation. But for us, most of the time, this is just a rather technical details, and it doesn't and it doesn't affect much what we're doing. So that's why I'm just gonna work with the untwisted version. So for the treatment of the twisted, you can find it in the paper on the archive. But yeah, but for our purpose of the talk, it doesn't play a big difference. Cool. So now, so yeah, so far I've tell you a recipe that like form a local function and a polarization to obtain an ideal of the Witt algebra. Obviously, there's things that we need to check, like for example, whether polarization exists or like whether the ideal we get is a primitive ideal. But so our next theorem say that like everything worked really nice for W. So let chi be a local function on W. There always exists a polarization P of chi. So I just want to stress here that like one of the main reason why the orbit method is not sort of like um, generalized very well to other class of the algebra is that then there might not always exist polarization for every element of the dual space, but for us it always exists. Um, and moreover, like there are a lot of them. Um, but thankfully, Q chi, but thankfully the ideal Q chi, the annihilator of the modules, is independent of the choice of the polarization P. So from now on, so I can drop the dependence on the polarization on P on the dependent on P now, and then just calling them Q chi. So now all Q chi are completely prime ideals of U of G. So we prove yeah. Thus we now so this in particular says that the recipe do what it say that it gives us a primitive ideal of U of W. Thus we have now defined a map from W star to the primitive spectrum of U of W, where I send a local function to Q chi, the annihilator, and a non-local function to zero. So zero is a primitive ideal in prim of U of G, and this is not a trivial result. This is the result by Oliver Matthew. Yeah, I think back in the 90s. Yeah, and then it's later proven again by Sue in one of her paper. Yeah. Um, yeah, so I just want to mention that so when I when I finished the paper and then put it on the archive, and then Sue sent it to Oliver, then so we didn't know about Roseanne Uro, Uroshiro Ushiro Bira paper in the 90s, 98. So we weren't aware of her paper. And then when I put it on the archive and then Sue sent it to Oliver Matthew, then he told us about Roseanne's paper um, here. Um, Yeah, but our proof are independent, and yeah, her proof is very nice. And so our proof is a bit computational, but it's a bit more explicit in her proof than her proof. Her proof is like is a stronger argument, more general argument than our. But in particular, we prove something that she didn't prove, that the Q chi is independent of the choice of polarization P here. Um, oh, right, and yeah, this is the main result of her paper. She has a conjecture which surprisingly we managed to prove it. Yeah, as well. So thus, we now have a candidate for the Dix-Mean map. Um, So remember, as before, we have the natural map from W star to the Poisson primitive spectrum, where where I send a local function chi to p chi, um, and the map from W star to the primitive spectrum U of W, where I send chi to q chi. So a natural question here is that whether there exists, where this is the map that we're looking for, um, that there exists a map from P prim of S of W and prim of U of W. So Roseanne's paper sort of ends here, where she conjectured that this map is well defined, and then indeed, like in our paper, we proved that long Dix-Mean map is well defined. So if you have p chi equals p eta, then indeed q chi is equal to q eta.
Excuse me, is this d of x surjective? Or do we know?
No, we don't know that yet. I'm gonna say something about subjectivity later. Yeah, but this is a really good question. We don't know whether this is subjective. This is like what we really hope to understand. Yeah, but but right now it's not subjective. We just know that it lands in the primitive spectrum space. Thanks for the question. So for the rest of the talk, I'm gonna sort of like go through a proof sketch of this theorem, and yeah, because I think this theorem has a really nice proof, and then it is like yeah, and then there's more more ideas in the proof. So now let's Gn be a finite dimensional solvable Lie algebra generated by V0 to Vn minus 1 with the following Lie bracket, where Vi, Vj is j minus I, Vi plus j, if I plus j is less than or equals to n, and 0 otherwise. So if you sort of remember the Lie bracket of the Witt algebra, this looks exactly like it. So in fact, the Witt algebra is a simple algebra, so it has no ideals. But then I can take the subquotient of W. So this Gn is just a subquotient of W, where I choose all the V, all the things that are bigger or at least n. Okay, and now another algebra that I need is a Y algebra with the relation del t minus t del equals 1, and then I localize it at t minus 1. So I add the inverse of t in. So Here I'm using notation slightly because when we all know that when we use sort of when we write polynomial like this, then it's not then it's commutative. But like for the purpose of this talk, I'm just gonna write it like this. Yeah, but this is the localized Lie algebra, and then I take any 1 point local function on W. So this is the main um, sort of idea in the proof that we managed to construct a graded ring homomorphism from U of W to this new ring here, which is like the tensor product of the Lie algebra with the universal enveloping algebra of a finite dimensional algebra. So this image here is much smaller than U of W in particular. So where the map is so the reason why I want to include this the formula of the map is that it looks really similar to the way we define local function. So where I send f del to f times del again, and then now I'm taking the sum of from I equals 0 to n minus 1 and f to the I plus 1 derivative, quotient now by I plus 1 factorial times vi. Remember, vi is the basis of the gi here, of the gn here. So yeah, so this is a graded ring homomorphism, and moreover, this is the universal. The psi n is universal in the sense that the kernel of this map psi n is the intersection of all q chi, the annihilators, where chi is a local function of order n. And then we can stronger this result by saying that this is furthermore the intersection of all primitive ideal q chi, where chi is a local function of order at most n as well. So that this map psi n is indeed the key ingredient in our proof for the strong Dix-Mean map. Okay, so now the last step in our proof is that we prove that there exists an element, and now we call them chi bar because it's closely related to chi, which is an element of the dual space Gn and a corresponding primitive ideal Q chi bar of U of Gn of this now solvable finite algebra, such that Q chi is the inverse image of the tensor product of the Lie algebra with this Q chi. And now this allows us to complete the whole story. So let's Gn now be the adjoint algebraic group of Gn. So now recall that our Gn here is finite dimensional solvable Lie algebra. There exists an adjoint algebraic group. Okay, so we assume Q chi equals P chi equals P eta. So what I mean by closely related is that you can prove that the coadjoint action of Gn on chi bar equals the coadjoint orbit of Qn on eta bar. So that's what it means to be closely related. So we can prove this. And remember that Gn is a finite dimensional solvable Lie algebra. So our normal Dix-Mean method works. So what it means is that the Q chi bar here from the classical Dix-Mean method equals to Q chi bar equals Q eta bar here. And then by this formula, we managed to prove that Q chi equals Q eta. And then by going through this process, you can prove that Q chi equal. When P chi equal P eta, then Q chi equals Q eta. So yeah, so what we've done so far is define a strong Dix-Mean map, dx twiddle, between the Poisson primitive spectrum S of W to the primitive spectrum of U of W. And this is indeed an instance of the orbit method. So the case for the Virasoro algebra is analogous as well, where here the Virasoro, I guess maybe here, where the Dix-mean map here is you send Q local to Q chi as well, and chi not local to the ideal generated by Z minus chi of Z. Yeah, but the point is we can do the same for the Virasoro algebra. So now a natural question, or like that Zara just asked, is whether the X twiddle is surjective. And this in particular is, and if it is, then this is a very strong statement. So what it says is then every primitive ideal of U of W is completely prime, because the ideal we constructed, the Q chi here, is a completely prime ideal. So what it says is that every primitive ideal of U of G is completely prime. And moreover, W satisfies the ascending chain condition on primitive ideals. We know that the strong Dix-mean map, the X, is unfortunately not injective, but how non-injective it is, we're still trying to sort of prove, to classify all instance where injectivity fails. The next question is the X twiddle a continuous and open map? As I said before, they're a natural topology one can define on the Poisson primitive ideals and on the primitive ideal of U of G, on U of W. So a natural question is whether the map I'll define is continuous and open map. And lastly, so the image, so the map psi n here is a very nice map. And a question is, what can the image or the kernel of the map psi n can tell us about U of W? So this is this is a very nice question. So if you so my supervisor Sue Sierra and Chelsea Watson proved that that the Witt algebra, the universal enveloping algebra of the Witt algebra, is not a Noetherian ring. And then, so one of the way you can see that is that the image of this map psi 1 is not a Noetherian ring. So that will give you that the Witt algebra is not Noetherian. So a natural question is that to study the image and the kernel of these map U of W, and then try to understand whether we can say anything else about like are any properties that can be pulled back from the image of W in this way. Yeah, that is it. Thanks for thanks for listening to my talk.
Okay. Thank you, Tuan. Thank you for the very nice talk. Right, so I will open the chat on the side to see something. So are there any comments or questions from the audience?
So can you say anything, can you give a conceptual explanation of the map psi n, where it comes from? Do you have anything like that?
Where it comes from?
It looks kind of like an exponential map in a way.
Yeah, I think to be honest, this map, we didn't know that it exists before working before too deep in the project, And I think I just sort of stump on like happen to find it like when working with small examples and then sort of pattern emerging. Um, and then we conjecture that such a map exists because of the way we define local function, sort of like again taking like the nth derivative and the sum of the nth derivative, like this formula here. So we sort of like think that such a map exists. And then, yeah, at the end, we managed to prove that it is indeed a graded ring homomorphism, but a more conceptual way. Um, yeah, unfortunately, I don't know. So there is indeed sort of an infinite version of this map
Hmm.
where I map U of W to the product of the Y algebra tensor U of so if you like, is the W bigger than or equal to zero? Is the
Yeah.
Witt algebra the positive Witt algebra? Just so where I just take the infinite sum, um, and we indeed managed to prove that for that map is well defined. And then when you take the quotient down to Gn here, then it factors through. So when you take the quotient from, so this Gn are ideals of W0
Yeah.
bigger than or equals to zero. So when you take the quotient down or the projection down, then that map psi infinity will sort of give you this map psi n. So I guess that is in a way sort of explain a bit about this map psi n. Yeah.
I see. Thank you.
And yeah, obviously, like in your work and with Martin, or I don't know whether this map is defined earlier, but you have sort of the psi 1 and the psi 0 map where
Yes. Yes.
yeah, where you map f del to f del plus f prime, and yeah, this is just like sort of a more going more and more taking more and more derivative of f there.
I'm actually here in Edinburgh, so maybe we can talk.
Yeah, yeah. Thank you.
Okay. Any other questions? Not. Tuan, do you have an example where the strong dx map is not the injectivity of that fails? You said
Oh yeah.
yeah. Is it obvious or
Yeah, I can explain it hopefully. So here, like I say that all QI are primitive ideal of U of G. So
hmm?
one of the reason why I don't say that, like for example, this module M chi P, it's just a simple modules, or like an irreducible representation of W. This is
Mhm.
not true in general. So when you take chi equals um um yeah, I think this is like again like one of Conley's result, Charles Conley result as well. That when you have chi is yeah, here maybe I have the formula for chi. Yeah, so when you have that chi is x01 here, for
Mhm.
example, and chi x1. So one function I'm sending f del to f prime x, and then one function I'm sending f del to f of x, then I think one of them is not simple. The zero function is not simple, I think. The modules induced by sending f del to f del is not simple. Um, but the annihilator of these two representations are the same. So in particular, you can replace the non-simple or non-irreducible representation by an irreducible representation. Um, Yeah, and yeah, and then I think this is, and then obviously this would generate a class of example where inject fails. Like you can take tensor product or sums of these local function together, but we conjecture that this is all instant where injectivity fails.
Okay.
Yeah.
So, and I mean, it seems to be building on quite a lot of specific results for Witt and Poisson primitive ideals of the symmetric algebra of Witt, I guess. Do you expect this can be? I mean, there are general techniques to be extracted for other infinite dimensional algebras.
Yeah, I think sort of one of the nice thing about the Witt algebra is that surprisingly what we've done so far is that the Witt algebra behave really similarly to solvable Lie algebra.
Mhm.
So my guess is that it would work for like sort of like infinite dimensional Lie algebra that behaves sort of like solvable Lie algebra.
Mhm.
And I think the process probably goes through the same construction. That I think the main thing is to find such the map psi n here that
Yeah.
sort of like map on a big infinite dimensional Lie algebra to a sort of much more manageable solvable Lie algebra here. And I think like once we can do that and then we have some understanding about the Poisson side of that, then I think yeah, it would work the same way. Um, yeah. Yeah, but for now, I think the main thing is that we don't know whether such a map psi n exists for all infinite dimensional. Um, yeah. I think Sue's oh no, it's slightly different. Yeah. Okay.
Okay, very interesting. Thank you. Are there other questions or comments that people want to ask? Okay, so if not, thank you everyone for attending. I guess there is a seminar next week as well, as every Monday basically. So same place, same time. Thank you. Thank you, Tuan. And thanks again, Tuan. I think we should thank Tuan again for his lovely talk. Thank you.
Thanks everyone for listening. Yeah, and thanks for having me.
Thanks, nice talk. Bye.
Bye.
See you.
Are you still recording,